Connecting the angular quantities and the linear quantities so far has been pretty straightforward and makes for a very nice pattern. Here we had the angular displacement multiplied by the distance to the axis of rotation, and that gives, in essence, the linear displacement. Or here we have the angular velocity multiplied by the distance to the axis of rotation, and that gives the tangential or linear velocity. It would be awfully nice if acceleration followed the same pattern, but acceleration is more complicated than that. Does it follow the same pattern? Well, the answer is a little bit yes and a little bit no. Let's consider a circle, and center of the circle is the axis of rotation, and we have a point in a larger object, or it could be a car going around, salute a traffic circle or something like that. It's moving along, but let's suppose that it's speeding up or slowing down. Certainly it's changing its direction. It really has an acceleration regardless. But let's put this on kind of that tilted coordinate system that we had in the last section. Where we have the radial axis and the tangential axis. But the object in accelerating, if it's truly speeding up or slowing down, its acceleration is general enough that it may, for instance, have to draw something here. It may, for instance, be a vector-oriented, something like that. So it doesn't lie necessarily on the tangential axis. It doesn't lie necessarily on the radial axis. It's a more general situation. However, just as with any vector, we could break it down into the components. And if we look at the part of the vector that's down in the radial axis, well, I'd love to call that a sub r and say that's the radial component of the acceleration. But actually, it's often called the centripetal acceleration. So we're going to go with that. Centripetal means pointing towards the center. And if we consider this more or less as a vector, that part of the acceleration is pointing towards the center of the circle, and hence the centripetal acceleration. It also has, we'll be ingenious and even try a different color here, see what happens. We can also take this vector and look at the projection in the tangential axis, and this one really is going to be a sub t. So we have the tangential acceleration. And in fact, the tangential acceleration continues the pattern that we established above. The tangential acceleration is going to be the distance to the axis of rotation times the angular acceleration. The pattern holds up. But the centripetal acceleration is a little more complicated, or it's certainly different. I don't know that it's more complicated. But that is equal to the tangential velocity squared divided by the distance to the axis of rotation. So two different formulas for the components of the acceleration. One continues the pattern. The angular quantity times the r is going to give the linear quantity. The other one, however, just totally breaks that pattern. Sorry about that. The book does like to point out that these really are components of acceleration. They're not new kinds of acceleration. It's the same old linear acceleration. And one way that it illustrates that is to say that the magnitude of the acceleration, just like before, it would have been the ax squared plus the ay squared. Here we could do it as the centripetal acceleration squared plus the tangential acceleration squared. A couple more comments here. would be that the tangential acceleration is the part of the acceleration that causes the object to speed up or slow down. The centripetal acceleration, on the other hand, is the part that causes the change in direction. And in fact, it's the centripetal acceleration that accounts for the circular motion. And an additional comment here, if the tangential acceleration is the r times the angular acceleration, well, this is going to equal 0 if alpha equals 0. The angular acceleration is 0. Or that would also go along with constant angular velocity. So if an object is moving around in a circle at a constant rate, it's not speeding up or slowing down. The tangential acceleration is 0, and the centripetal acceleration, well, that still has a value. That's what's causing it to go around in a circle. That's in essence the velocity squared divided by the r. But in the case of constant angular velocity, this is the only aspect of the acceleration. That's kind of interesting, I think, and that hits that section, knocks it right out of the ballpark.